Good afternoon, everyone. My name is Allie Toltz, or Allison Toltz. For anyone who doesn't know me, I'm a clinical physicist here at McGill and also a former McGill student and graduate. And it is my absolute pleasure to both introduce and thank our speaker for being willing to do this talk today, well after hours for him because he is in the UK. This is Dr. Sam Flynn. He got his PhD at the University of Birmingham and is a higher scientist at the National Physical Laboratory in Teddington, UK. And he's going to talk to us about dosimetry and calorimetry for ultra-high dose rate radiotherapy. Take it away, Sam.
Cool. Thank you so much for that. Yeah, dosimetry is the main focus of this talk, but I'm going to try and branch out to a bit of other things when it comes to it. So my name is Sam, researcher at the National Physical Laboratory. Some housekeeping before we start is that the transmission calorimeter design has been protected under a priority patent, and some of these results are pre-publication, so they have yet to be peer-reviewed. The way that this structure is going to roughly go is I'm from the National Physical Laboratory, and you might know what that is, so I'm going to give a bit of context and explanation for why I'm here today, like what the focus of our company is, and why we're interested in this. I get to talk about calorimetry, which is my favorite topic in the world, talking about flash radiotherapy, less my favorite, but still very interesting. And then that's going to lead me into some of like the new developments that are actually happening for calorimetry for flash radiotherapy. So the National Physical Laboratory is the United Kingdom's National Measurement Institute. We are responsible for the realization and dissemination of primary standards to support the UK industry. Primary standards, if you're not aware, are the meter, the second, the kilogram, that kind of thing. Are the main SI units. Is we realize them here at NPL and disseminate them, whatnot. It's a very broad type of things that we do at this company, of which the radiotherapy department's only about 20 people. It's very versatile, but it's very interesting amount of different activities we have. The counterpart in Canada is NRC, National Research Council, with different focuses. So depending on like different national interests or not. We are based in southwest London, sunny Teddington, next to Bushy Park. If you ever get the chance to come visit this area of the world, do let us know. We'll happily give you a tour of calorimeters and show you around our lab in person. We are very active within the medical physics community in the UK. We don't just sit in our lab and send chambers out once every few years. We are as involved in the community as the community will let us. So we directly support the National Health Service in the UK through direct collaboration with IPEM, which is the regulatory body for medical physicists in the UK. There are several members of our staff that are clinically registered medical physicists. It's a protected title here in the UK. And we have that clinical expertise within our group, ensuring that our calibrations are relevant to the community. We do training for therapy physicists. We'll do this both in MPL and in the clinic, depending on what the user wants. We'll do audits for hospitals, providing independent dosimetry support, whether that's alanine or full end-to-end patient workflow, or cell degrees, depending on what the clinic is after. But at the end of the day, we are a standards laboratory, and it comes down to calibrations. We love our calibrations, that's what we're famous for. For radiotherapy, traceability is essential. You should all be aware that the primary standard for the primary measurement unit in radiotherapy is the gray, and this is realized at a primary standard and then disseminated to the community. Here in the UK, hospitals will send us their ionisation chambers, and we will calibrate them against the primary standard. And by doing so, there's a traceable link from our realization of the gray to them using it in the clinic. There are several procedures or codes of practice for how you do this. We've got bespoke ones here in the UK for high energy photons and electrons, but on the continent you've got TRS 398, or I know you guys are very familiar with TG51. They're very similar, minor tweaks, differences, but the overall premise is the same of how you go from a standards lab to using the clinic. Because you have this chain of calibration, one measurement is dependent on the other. Any uncertainty that is done at the primary standard level is inherited by everyone else down the chain. So if the primary standards lab has a 5% uncertainty, by the time it's used in the clinic, you have a 5% plus whatever else is added in the chain. So it is really important for us at the primary standard level to minimize that as much as possible to give the best quality care we can get to a patient at the end of the chain. In the National Physical Laboratory, we use graphite calorimeters for our primary standard measurements. This is a photo of our graphite primary standard calorimeter. And calorimeters are really simple devices. I'll show you the equation shortly, but energy is deposited within the sensitive volume, which is the core. It causes a small temperature rise, and if you can measure that temperature rise, you can work out the dose that was delivered to it. These devices are operated typically in, we call it quasi-adiabatic mode, in which the temperature is allowed to sort of drift, but in a controlled manner. And then we do a fitting technique between before and after the beam to work out the midpoint and extrapolate the radiation-induced temperature rise. Here's a CT, a radiograph of the calorimeter, showing all the different bits and gubbins that are in it. There are an array of different thermistors, some of them for heating, some of them for sensing, and it works very well for us. We've got different calorimeters for different purposes, but they all are based on the same core concept, which is based on the Doman design from the 60s, which was originally from NIST. At MPL, we're using graphite, but we are within the NMI community, we're broadly split between using graphite and water. There are advantages of doing it both ways, and it's important that not everyone does it the same way, because if everyone did, then there'd be no way of independently validating each other. Because we are not calibrated against anyone else, the only way we can check if we're doing okay is we do audits against each other. But at the end of those, we don't provide each other with a correction factor. If someone else is off or below or something else is wrong with the measurement, we don't say give a 10% factor to your measurements to make it in line. It has to be done straight from first principles. So yeah, we use graphite, many advantages towards that. The main one being, if you go back to the equation that links dose and temperature rise, the factor that links the two is the specific heat capacity. Now, graphite's specific heat capacity is about a sixth of that of water, which means for the same amount of radiation dose, you get 6 times as much signal. When you're delivering a clinical radiotherapy dose delivery, say 2 gray, in graphite that will result in a 2.5, maybe 3 millikelvin temperature change, which is very, very small and difficult to measure. And if you want low uncertainty on that, you got to do it many times. And so anything you can do to improve the quality of that measurement is a win for us. That's why we've gone for graphite. You get more signal for the same amount of dose. It has some other advantages as well. It's easy to machine. You can thermally segment it into different volumes, and it's a lot more portable than having a large water phantom. So our calorimeters, we've taken them around the world, around most of Europe. There is obviously a downside, being that within the clinic, the quantity of interest is dose to water, not dose to graphite. So our largest source of uncertainty is actually our Monte Carlo conversion factors. This conversion of dose to graphite to dose to water. And it's something that's kind of inherent with graphite calorimetry, but from our perspective, the improvement on the quality of the data counteracts that. And it eventually almost balances out between us and water calorimetry. They have worse signal to noise ratio, but we can get more data. So it's about even. And again, importantly, it's an independent method of doing it. We have an array of calorimeters here at NPL for different purposes. Some of these are established and we've got code to practice for, but some of them are still in development. We've got X-ray ones, electron ones, brachytherapy ones, proton beam therapy ones. They're all for different shapes and sizes. I'm going to talk to you now about what we're doing for ultra-high dose radiotherapy and calorimeters in that. So I assume that you've never heard of ultra-high dose radiotherapy before. You've lived under a rock, you've not read any journal papers. Flash is new to you. Flash is the concept of delivering a normal radiotherapy dose, but in a fraction of the time. It's the same integral dose, but on a much higher dose rate compared to conventional radiotherapy. The term flash is specifically a biological effect, whereas the modality should be called ultra-high dose rate radiotherapy, just to distinguish the two there. But UHDR has actually been around for quite a long time, 1960s, but it was only in the 2014s when a very impactful paper came out just showing that delivering the same amount of radiation but faster results in sparing for healthy tissue. And since then it's resulted in an exponential array of more papers are coming out to deal with this. It's very interesting from a radiobiological perspective. If you haven't seen this, this is a 2019 paper showing that the same dose delivered to pigs at different dose rates changes the side effects that are resulting from it. You get necroses at conventional dose rate, but minimal or nothing at flash dose rates. So there's a lot of community interest in that. That was 2019. Since then, we've had a patient treated with UHDR electrons. This was a superficial tumour, just validating the safety of it. And we've had the world's first Proton clinical trial. This was in Cincinnati Children's Hospitals using shoot-through protons. That went well. They've moved on to the second phase of that, FAST-02. And yes, just painting the picture for you, there's this wealth of activity happening here for flash radiotherapy and the community interest. Mainly it's down to the radiobiological. The current mechanisms of flash aren't understood correctly, but yeah, there's people interested in it. We are not a radiobiology lab here at MPL, we're a dosimetry lab. And the reason we're active in this area is because dosimetry in flash ultra-high dose rates is really hard, essentially. There is a concern that people doing it will do it wrong, and that leads to maybe animals wasted. It leads to a slow transition of a study towards being clinical ready, or just an abandonment of the therapy altogether. So it's in our interests to make sure that all these people doing flash work do it correctly. The source of the difficulty comes from a phenomenon called ion recombination. So if you're not familiar with how ion chambers work, the fundamentals is that you've got two plates, typically parallel, but you can have different shapes if you want. You have a potential difference between them. And as an ionizing particle, gamma, photon, electron, it goes through, it will strip an electron from an air molecule, and then if you have a potential difference across this cathode and the anode, you can measure that as a charge. Here's another example of that. There are two forms of ion recombination. You have initial recombination, which is when the ion pairs that's created will join back with itself as part of the same track, and that is particle dependent. So that depends on whether you've got using a carbon beam, low energy X-rays, and it's pretty consistent. It's much more dependent on high energy, high LET particles, such as alpha, more prominent for that. But for the most part, it's not as much of a consequence. The more troubling one is called general recombination, which is when you have ion pairs from different tracks interacting with each other and cancelling each other out. This is dose rate dependent because it's dependent on the number of tracks that you have. If you flood a volume with lots of particles at once, they're going to start interacting with each other. Here is a very nice figure from a graph by Christopher Peterson showing that the ion collection efficiency of an electron chamber goes, it just tanks basically. As soon as you get above 0.1 gray per pulse, your collection efficiency drops down to less than 20%. There's a paper by Manus showing that in the worst case scenarios, you can end up with collection efficiencies of less than 3%. And again, but going back to the concern that MPL has, if you're going to try and correct for this, there are many techniques. You can use the tooth voltage method. How certain are you in this unique factor? If you're having to multiply your signal by a factor of 20 or 30 to get a correct value, then you've got to be really, really confident in the certainty of that. You might have a really, really good calibration in your ion chamber, but if your correction factor is uncertain, then you're not going to have a good idea on how much dose you're delivering to a patient. So make sure you get it right. Don't overdose and underdose a patient. Be really certain of your dosimetry. There is obviously some instruments that aren't dose rate dependent, that don't have this ion collection efficiency like ion chambers do. I've spoken about them earlier. It's my favorite. It's calorimeters. Because we're just putting radiation into a medium and causing a temperature change, more radiation faster isn't causing any issues. If anything, it makes the calorimeters perform better. Our second largest source of uncertainty that we have for calorimeters is heat dissipation, and like heat from one component flowing to another and distorting the two. Whereas in flash and ultra high dose rates, because the beam is delivered to us so fast, there's no opportunity for that to happen. So our uncertainties actually get better. On the right hand side, there's a temperature profile plot from one of our measurements we did. This was at the Children's Hospital in Cincinnati. So we took our proton calorimeter there to do an independent dosimetry audit for them, and that allowed them to get FDA approval to start the FAST-01 trial. We're really proud of this, and we use it all the time as a demonstration of look, calorimeters are useful for ultra high dose rates. There is a potential for them to be used in this. Everyone should get a calorimeter. Go out and buy one from your local shop. It is obviously a lot harder than that though. There's a reason that not everyone has calorimeters and that chambers are used in the practice. Calorimeters are really difficult to use. You've got to have fitting expertise. You've got to understand the different heat mechanisms. They're not simple devices. They're really expensive as well. And a good chamber might cost you a few £1,000s. My calibration, another several £1,000s. And the electrometer, nice one, say £10,000. You're looking at a £20,000 total budget. But that might get you the cost of one of the precision digital multimeters we're using for the calorimeter. So it becomes impractical for a clinic to have its own calorimeter. It doesn't really make sense. They're also quite slow to operate. An ion chamber can be used within several minutes of getting out of its case, whereas a calorimeter, you're looking at an hour of measurements for most. And that's considered fast. It's an hour for us after setup to do an energy in a certain modality. If you're using a water calorimeter, you're looking at half a day at least. Calorimeters are also difficult to transport. You look at a little case that you have for an ionization chamber, you're looking at several flight cases for a calorimeter. And yeah, lastly, just calorimeters. Everyone knows how to use calorimeters. You've got the wealth of experience that physicists have for this. And we really think this is a major hurdle that would need to overcome. McGill famously invented the aero calorimeter, which is a fantastic design of different calorimeter regions with different thermistors. So it's a really elegant solution. But the trouble I think this calorimeter had was just displacing that established marker, and that was in conventional radiotherapy. Maybe it was a bit too hard to beat calorimeters. And although I do know they're doing some more flash dose rate stuff coming up. So calorimeters are difficult, but maybe they don't have to be. Maybe even the aero is a bit too complex. Maybe a calorimeter for dummies could be made. And that was our initial approach. Next thing I'm going to present, which is how simple can you make a calorimeter and it still be useful for a clinical measurement. So this is it. This is our secondary standard calorimeter. The active volume of it is just a simple graphite core. It's 16 millimeter diameter, 2 millimeters thick, with a single thermistor in it. We're not using aerogel or anything to thermally isolate it, we're just using air, and it's made out of a 3D printed case, PMMA 2 halves. You stick them together, you lacquer it to make it waterproof, and then it's done. I mentioned earlier that the electronics is a major hurdle that needs to be overcome, and so let's simplify that. We replaced it with a simple DC Wheatstone bridge. If you aren't familiar with how this works, it amplifies a small change in resistance to make a larger change in voltage. And we used off-the-shelf components for that. We used a cheap digital multimeter. This costs about £1,000. And the circuitry for this was built on a breadboard. It's really, really simple. It's like something that a high schooler could do. We calibrated this in terms of temperature, and then we placed it in a water tank, in solid water in front of our electrolyte. So we've got one linear carrier NPL that we use for our calibrations for all the different services we provide. And yeah, we calibrated this secondary standard calorimeter against a Roos chamber, which was calibrated against the primary standard electron calorimeter. We did it as if it was a Roos chamber. Obviously it's not, it's got different designs and whatnot, but it's got the same water equivalent thickness building up to it. Yeah, otherwise that works well. So this allowed us to get a Gray per Kelvin calibration factor of the secondary standard calorimeter. This is odd for a calorimeter because normally you use them and you realize dose in its absolute form. There's no calibration, but here we are converting it from one to the other. At this point, we have a calibrated calorimeter. We need to do some tests with it. We need to prove it works. We know that UHDR is where it's likely most beneficial, so we've collaborated with an institute in Italy, and they threw in the electron beam for us. This is an example of the results we get. So the y-axis, you've got temperature, and the x-axis, you've got sample number. It's about 5 hertz per second, 5 hertz. You can see you've got a thermal drift as it's happy idling. The beam will come on, you get a sharp spike, and then after the beam goes off, it goes back to idling. It's quite happy again. And all we need to do with this result is just extrapolate to the midpoint and calculate the radiation-induced temperature rise. An interesting feature of this one is that because the thermistor is directly being irradiated, the temperature after the flash irradiations is slightly higher than the graphite around it, and you can see that as a small decay. That's not a problem, it's built into this calibration factor. This is neat, but it's not quantitative, so I gave you some numbers now. We compared this against alanine, which is in the same position, and did a variety of dose per pulse measurements. We saw that it agreed within 0.4% compared to alanine, which is phenomenal for a device that was 3D printed and built by hand. Just again, covered it in varnish, made it waterproof. What is really exciting for us as an NMI is that it's a completely independent measurement. Because the secondary standard is traceable to the electron primary standard versus the alanine, which is traceable to the photon primary standard, it's two independent methods, which is great for us. We can be confident in what we're delivering. Digging more into the numbers, if you look at the uncertainty between the secondary standard calorimeter and the alanine, the uncertainty is actually lower in the secondary standard calorimeter, kind of proving more to us that there is something here, that there is a use case for calorimeters in ultra-high dose rate radiotherapy dosimetry. Now, alanine has, if you're not familiar with it, it's a chemical dosimeter. It's very shelf stable. You can post it back to your NMI of choice and read out what the dose was delivered months later, if you don't have the expertise or the time to work out the dosimetry. But having this as an online check for how much dose you've delivered for your machine could be really useful. So we're excited about that. It got us a lot more into the, all right, we've got calorimeters in Flash. We're changing the definition of what calorimeters are used. What more can we do with this? Can we do anything weird? Can we change it up? So, yeah. The focus of the secondary standard calorimeter is on reference chambers, which struggle and are the workhorse of modern radiotherapy. But they aren't the only ionization chamber within the medical physics ecosystem. The other one being monitor chambers that are part of a dose delivery system. And we know that they experience the same ion recombination effects and uncertainties that need correcting for. So how do we put an ionization chamber into a beam delivery system? What changes are needed to make it fit? Here's the cross section of the calorimeter I showed from earlier, but let's simplify it, just make it nice like this. This design works really well at isolating a very small temperature change. Because we've got a small core that is shielded by, we call them jackets, it's very difficult for the environmental changes to impact the core directly, and allows us to get this really stable environment to measure dose accurately. Now, you put a beam through it and you're going to lose a lot of it due to attenuation. If you're being very, very pedantic, this is technically a transmission device. The FAST-01 study we did with Cincinnati, this was the proton calorimeter. It's about 5 centimeters water, 5 centimeters thick, about 10 centimeters water equivalent. Is a transmission device because it was operated in the plateau. So if you had a patient behind it, maybe you could, but that doesn't satisfy the clinical requirements for what a monitor chamber is. Typically that's 2 millimeters water equivalent thickness or less being ideal. So it's going to pull our beam up to something where it's not. The obvious answer for this is if we're not going to they're not going to increase the amount of energy of the proton machines just for us, is we're going to have to lose some material so that the beam is perturbed less, so there's less scatter, so it appears more invisible. Voila, we have an empty core. And this would satisfy our requirements of having a thin calorimeter, but now we're in the circumstance where we're going to start losing heat to the environment. We've got a very small temperature sensor that is exposed to fluctuations. The way we've got around that is by surrounding it with a mylar jacket to attempt to shield it from the environment. Now, we know that this won't be as good as a nested graphite system. There's a lot more infrared that will get through. It's a lot more sensitive to changes. But the question we wanted to ask was is that going to be a problem for ultra-high dose rate radiotherapy? If we lose temperature, that radiation-induced temperature rise over the course of several minutes, but our delivery was in the second regime, that's not necessarily an issue. And so I thought, all right, we'll build it, we'll see what happens, and we'll do some evaluations of it. So I am so proud of this instrument, and I love to show it to everyone I can, but this is the first transmission calorimeter we built. It is using supermarket aluminium foil as its sensitive core region, and it's held in a CD case, which I bought from a charity shop on the high street. It's using polystyrene film to enclose the air within it, and this aluminium core is held in the air using 4 thermistors. The tension from the wire of the thermistors is what thermally isolates it from the environment. This is measured to be about 0.6 millimeters thick, which is about 1.2 millimeters water equivalent thickness. So it satisfies that requirement for a monitor chamber. This is technically a dose area product calorimeter because it is larger than the beam that it is measuring. We envision that if you were to ever use this, not that I would recommend using this particular device, but you'd calibrate it in terms of temperature change, which would be done against a device at reference conditions, similar to how you would with a monitor chamber, in terms of monitor units or something. The readout for this device was designed to be compatible with the secondary standard calorimeter that I showed earlier, using the same circuits. Those 4 thermistors that I described, they were all networked to provide an average thermistor value for the core. Because they're all thermally conducted to each other via the aluminium, there was no benefit seen from individually addressing them, although you could if you were particularly inclined. The first tests of this device were done at the University of Birmingham. They have a 36 MeV proton beam that's normally used for cellular studies and radiation hardness tests for electronics, but they're also getting into dosimetry, and this is an example of the type of thing that they can do there at this facility. We put the device in front of their proton beam nozzle and irradiated it with a nominal 40 grays per second. And this is the first result from that we've got from that. Y-axis is temperature, x-axis is time. And again, you get this, as the beam irradiates, you get this instantaneous temperature rise and then a decay afterwards. So I should point out though that I have kind of cheated and squashed the x-axis on this, and I'll show you that in a second. But other than that, it's the same profile that a normal calorimeter would have. You get a temperature rise. In fact, because the thermistors on this were slightly in the beam region, you get a slight bump as well, which is indicative that we're hitting something. This is the full set of data, and you can see that thermal loss to the environment again over tens of seconds. But tens of seconds is fine, actually. It's much longer than the time that the beam is on for, so it's not an issue potentially for us. It's very reproducible, as you can see here. You've got a nice set of 10, and it's just really sensitive. I've had to crop the y-axis on the about 500 seconds mark because we placed a piece of radiochromic film to measure the beam size, and the act of doing so, the film slightly above room temperature from being held, shot it up to half a degree more than it was normally. But I'm going to show you some quantitative results again. The response of this was compared against a Faraday cup, being dose rate independent. A very linear result. That's what we're hoping. There's no reason that dose wouldn't be proportional to temperature with an instrument like this. We have kind of validated that a straight line is a straight line, but we have shown that this kind of instrument could be used. Radiation-induced heat is lost in 30 seconds, so there's no way you could use this for conventional therapy. If your beam is getting close to a duration of 30 seconds, you're not going to get anything useful from this. And it was very sensitive to ambient fluctuations. The exposure room at Birmingham was very nice and very sealed. There's not air conditioning in there, so it is almost the best case for doing this kind of measurement. It doesn't really replicate clinical use. But we're not dissuaded by this. We still wanted to see where we could go with calorimetry. This was the first generation. I'm going to skip the second and just present the latest work, which is on the third generation. We've moved away from taping thermistors to aluminium foil, and we're now with an aluminium PCB based design. This is the same technology that's used in street lamps, where you have an LED that's generating a lot of heat. You have an aluminium PCB, which takes that heat away to a heat dump. We're just repurposing that to turn the whole thing into a sensor. And they're never designed for that, but they're actually really suitable. That thermistor network I described earlier, we're now embedding that on the PCB. That allows us to reduce the electrical complexity of it and make them a lot more robust. It simplifies the electronics. We're also moving to an aluminized mylar system rather than just cling film. The reason for doing that is aluminized mylar starts to shield some of the infrared, which is known to cause temperature fluctuations. This is demonstratable in a lab environment, that if you hover your hand over it, you'll barely see any temperature change, whereas with the non-transparent mylar, you can see it shoots up. So it's moving in the right direction to being a device that could maybe be used in the clinic. This also does have a secondary, we call it a compensating ring, around the outside. So we've got a central core region, which the beam goes in, but then we've got a halo around it. And these two cores are designed to have the same area, so they're exposed to the same amount of air turbulence or infrared contamination. But by selectively, if you only put beam into the active one, you can start to isolate the signal between one and the other. We built this with flexible electronics in mind so that you can either do a direct electrical comparison of the two. If you're familiar with electronics, you'll see the circuit below. That's directly comparing the resistance of the inner ring and the outer ring. Alternatively, we can hook the compensating ring up to its own Wheatstone bridge and have a digital compensation. So that's an area we're still looking into, which one provides the best certainty, most robust. I'm going to share some results now of this. So we tested this at the University of Oxford's Flash Core facility. This is it's an old clinical linear accelerator from the 90s, I believe, that has been repurposed to deliver flash beams. And they do a lot of studies here for it, and it's a very validated beam. It's clinically relevant, it's 6 MeV, and they've got a robust dosimetry, well, traceable back to us as it happens, but system for doing their experiments there. The studies were compared against an ionization chamber, which is positioned in the beam halo, that will be sensitive to ion recombination, but being in the halo, it's experiencing a lower dose rate, so it's not as sensitive. Right. And here's some results from it. So on the left-hand side, I've got a temperature plot for you. You can see that the shed of temperature to the environment now is much slower. It's much able to retain that heat it's got. It's not as good as the secondary standard calorimeter or even the Proton primary standard, but it's a hell of a lot better than it was. And you start to see that in the uncertainty measurements. You still see the characteristic, slow rise of the temperature. We're no longer hitting a thermistor though, you don't get a spike. And the speed at which that ramp happens is a function of the size of the beam relative to the core, as well as the thermal conductivity of the dielectric, which is a material used to electrically isolate the thermistors from the aluminium. We show that it's linear. This device is very, very linear. Again, showing a straight line is a straight line, but there's no reason it shouldn't be. It's linear up to 100 grays, and with, in theory, no, unless you start to get to the point of melting aluminium, no maximum. You can keep going as high with this. So if Flash 2 were ever invented that delivers at gigagrays per second, like, this device could potentially be useful for it. This is obviously best case scenario though. This is 2 gray per pulse, which is very, very flash. You look at the pulses here are microseconds long, so this is mega gray per second instantaneous dose rate. This is the best case scenario where the calorimeter works really well, but an ionization chamber will struggle. And we saw that on the day when we did this, that the reference monitor chamber, it lost all its sensitivity because it wasn't able to do any relative measurements because it lost that headway. You can't obviously always do stuff at flash. You got to do it conventional and maybe work your calibration up to then. If your calibration lab is giving you a factor for conventional dose rate, you maybe want to transfer it to flash. So we did some tests with this at conventional dose rate as well, and kind of expected, but as you see here, it doesn't perform as well. It's a lot better than it was, but it's not perfect, and it's something we're still working on. There's the heat transfer coefficient, as heat is lost to the environment, becomes an issue at low dose rates, or more specifically for long duration beams. If we were to do this study again, I think if we delivered 2 grays rather than 10 grays, our beam duration would be about 20 seconds. I think we'd get a lot better results, but that requires another experimental campaign, which we are not in the process of looking at. The standard deviation of each of these measurements, you can see that in the flash regime it's about 1%, whereas it verges up to almost 10% at conventional dose per pulse. And not ideal, but every step is progressive. We're making our ways there. With this in mind, we believe we've done a lot to prove that you can make calorimeter into kind of an ionization chamber. So we had a bit of creative thought about what more can we do to make a calorimeter like an ion chamber? What would be useful for the community? If you aren't familiar with strip detectors, they're very common in ion beam therapy, and it's just lots of independent electrically isolated ionization chambers, which you can tell the position and size of a radiotherapy beam. It's useful for scanned pencil beams particularly. So we wanted to see, could something like that be done for calorimetry? Can we make some thermally isolated devices? Now, this isn't us just like having a go for the sake of it. Ionization chambers, even strip ones, will suffer for ion recombination. And if you've got a Gaussian beam, out of the points where you've got a Gaussian on the side, you've got a different level of ion recombination than you do in the center. So your very sharp pencil beam might be measured, or it's a lot wider with your instruments than it might otherwise be. And if you're doing that, that might get fed into your TPS or otherwise, and you might start to get the wrong answer. So the logic behind this was, if you have a dose rate independent method of measuring beam profile on the fly, it could be useful. there could be a real use case for this. So it's a really simple test we did. We only built one of these. It was built myself using glue, lots of strips, 4 of them, and we irradiated the center, offset it by a centimeter, and irradiated again. We weren't that interested in absolute measurements for this because it was at the end of the day, it's designed to be a relative instrument. But what we wanted to look at is the response of each channel as it was moved. And we see that if you don't irradiate a calorimeter, you see no signal. We found that it was thermally isolated, as we were really hoping for. The channels that we did irradiate more experienced a greater signal, and the ones that we saw that were expected to be irradiated less saw less. This was nicely validated with film, but it's just like great to see it in the actual raw data. Stealing more from ionization chamber technology, you can have segmented ion chambers. These are really common in this one in particular in electrolinacs, but just general X-ray linacs as well, where you have multiple segmented regions that are all irradiated, and then you kind of balance like the left versus right, the gantry versus target, to work out the size of your beam, or maybe if it's steered or getting too big. So we made a calorimeter that was 2 modules that were the idea that they were both to be irradiated. Again, to validate, like, could this be done? What would you need to do going forward? It's a very simple test. Again, irradiating the center, moving it offset and re-irradiating it. And we show that, yes, you can do that. Not shown as part of this, but the 2 calorimeters, despite being in close proximity with each other, were thermally isolated from each other, preventing crosstalk and contamination, but allowing you to get this really clean measurement. Very chuffed with that, really happy. That wraps up that experimental campaign. So I'm going to show you now the next stage, where we're going with this. So it's still going to be an aluminium PCB based design, but it's a little bit more robust with a bit more modeling thought before doing the design. Better electrical performance, we've improved the bridges even further. I can tell you more about that this time next year, but we're looking forward to that. Cool. So, what's the long-term plan for like novel calorimetry or MPL? You can start to do weird things, as I've demonstrated. Like, if you stop to think of devices of calorimeters as exclusively for a National Measurement Institute, and instead as just dose rate independent sensors, you can build them into weird shapes, and that does work. An idea that we've had is, could you turn this into a 2-dimensional detector similar to a CMOS detector? Possibly. And then you could do maybe like several of them back to back. You could work out a pencil beam. But then is that just dreaming? Like, is that actually of pre-clinical use? Are people going to need that, or is that just us dreaming and like throwing calorimeters into a problem where they're not necessarily there? So like, whilst the physics might check out and the technology might be almost there, we're looking into that. But I don't know, it's a really nice idea that like, if any one of you wants to like have a go at it, let us know and we'll see if we can collaborate. We're very much dependent on like, is Flash going to be the next big thing? Flash is very dependent on like as a foundation for this technology. If Flash isn't necessary, then ion chambers are good for like beam monitoring. This won't ever be better than an ion chamber at conventional dose rates. There's not really a need for it. And yeah, is there the motivation in the market to disrupt chambers? Like we saw what happened to the aero calorimeter. It's a very elegant, very good design, but maybe just chambers, even if it is a larger uncertainty, might just be preferable to the clinic, to the environment. We'll see. Other things we're looking at with this are whether we can actually combine this with other instruments that is a bit more palatable to the clinic. So we've worked with the University College London's quadprobe device, which is to build a multi-sensor in a box type instrument that could do all your QA at once. It's designed for proton beams, and the intention that it could measure the energy by measuring the range of the beam using scintillating detectors. It can measure the beam's spot and size using a CMOS device, and it could provide independent dosimetry using this transmission calorimeter. We did some proof of principle work for that just in March this year. Simon Jolly presented that at PTGOG, and it works nicely. You can see a synchronized response on all detectors, and they do correlate nicely with each other. Further work is ongoing with that, and like hopefully I can present some more stuff about that next year, like when we're a bit more mature. That's a really exciting thing for us. Maybe if the end outcome isn't transmission calorimeters in the clinic as part of routine QA, maybe it's involved in another instrument. I don't know the future of yet, maybe. Yeah, so to conclude this, like, Sarah, thank you so much for the attention you give me. You can do weird things with calorimeters once you start like thinking of them as non-prime standard level devices. You can start to make weird shapes to tackle this, like these emerging dosimetry problems. Current standard deviation isn't quite there, but we are getting there with our ideas. So watch this space. I do have to thank my funders, particularly the UK government, our collaborators, naturally, yeah, and I thank you for your time.
Thanks so much, Sam. Pete, can you help me turn the camera around? We have some time for questions. So that was so much information and a lot to think about. And also, like, thanks so much for your enthusiasm. It's really palpable. I hope it got somebody else as excited as I felt about it. Does anyone in the room have any questions for Sam? Don't be shy. Stunned audience.
And if you have a question in the Zoom, you can type it in the chat or just unmute and ask. We have a question in the room. Chris.
Yeah, hi, Sam. Thanks for the talk. It's very interesting. A little bit away from the calorimetry, there's something you mentioned at the beginning of auditing each other across national cities. I was just curious, have any of those audits ever failed, and what were the next steps taken?
I'm going to repeat that just for the recording and hopefully in case you didn't hear it. That was Chris asking, in the context of national standards labs and like international or in like audits, have there ever been any failures and what steps are taken after that? Is that all right? Repeat. Yeah.
Sure. To my knowledge, there's never been a failure. Everything always agrees. That doesn't mean like we massage the data to make it agree. Yes. No, I think at the level of being a national standards lab, like you look into everything so like robustly, everything so thoroughly that like you can't let yourself get to that step of actually being out of whack with everyone else. Of course, there are like discrepancies. People are within like 1% of each other, but no one's ever been like at an actionable level, at least in radiotherapy, to my knowledge.
I think I have a question.
Yep.
So some commented about the fact that some calorimeters might work if Flash is the next big thing. I would like to know his opinion. Will Flash be the next big thing? What do you think?
Did you get that, Sam?
did.
We're asking your opinion now. It doesn't have to be NPL's opinion. This can be your opinion.
So I am concerned that after many years of research into ultra high dose radiotherapy, that the exact mechanisms for Flash haven't been identified yet, and it does make me skeptical and a little bit worried. If you compare that to other therapies like spatially fractionated radiotherapy, which are maybe a bit newer, but have like expressed ways of this is how the therapeutic window is expanded, it does make me question Flash. But from putting my NPR hat back on, because the community is interested in Flash, we need to develop standards for it and like support them, regardless of like whether we personally think it's a clinically beneficial treatment. I think that was a very good neutral answer.
That was a brilliantly politically correct answer. I like that.
Very, very English.
What other opportunities are there for anyone interested in learning more about NPL or things that are coming up or getting involved in your lab if any of the students are interested in the future.
Thank you. So we have a workshop. We have 2 workshops that are happening in March, if any of you are interested. We have one on proton mini beam radiotherapy. The idea is to discuss the challenges that are preventing it from being clinical and like how do we overcome them as a community. The second one being targeted for supporting the clinical proton therapy centres in the UK, but we're very interested in outside perspectives and how we can improve. That's PMBT and PPRIG. If you're more interested in MPL as a place to work, we do have a vacancy opening in our group that closes next Friday.
What a chance.
All
I have a
right.
question.
Yeah, go on.
I thought of one. I'm going to turn it very low. Very nice work with I like the off-the-shelf glue, aluminum foil, CD case methods. And the prototypes seem to be working.
Yeah, no.
The transmission chamber in particular, I thought was a clever idea. The aluminum foil, did you just pick that because it's cheap and thin and you can measure it has a specific heat capacity that's low enough that you get a signal?
So the requirements of, I'll stop sharing. No, you can see it again. You get to see my calorimeter again. I'm that proud of it. So the requirements of this device were that it's thermally conductive because you want to measure the temperature of the thermistors from heating a body that's not part of the thermistors. It needs to have low water equivalent thickness, so that rules out lead, uranium, kind of restricts your metal choices that way. And it needs to be machinable. So a lot of our calorimeters use graphite, and graphite is difficult. It's not impossible, but it's challenging to make thin. It gets quite brittle. So that kind of gave us aluminium, and then you can buy aluminium really cheaply in a supermarket. And that was kind of the inspiration for, let's see how far we go with this. And now it has actually chosen to be a really good thing because we can leverage this aluminium PCB design. Aluminium just works better for us.
Okay. I have a crazy idea. Maybe I'm not the first person to think of it. What if you just had a thermistor and that was your calorimeter? Would that work?
Yeah, that would work. You'd have to directly radiate it. That would be similar to like having a diode somewhere in the beam to like measure the thing. That could work, yeah. The advantage of having like the transmission calorimeter versus just a single thermistor is any perturbation and scatter should be uniform with the transmission calorimeter, whereas you might create a shadow with thermistor. But if it's outside of the beam, like if you've got a large beam and you're sticking it within the,
Or you could do an array of thermistors. I don't know. I'm just thinking of other.
like
Make it as transmissible as possible. You want it basically to be air equivalent.
that would be ideal. Maybe you could do some like interferometry, measure the temperature of something without even like blocking it directly. Like maybe. We're just like getting weird with the technology now, so it's like, what more can we do?
Cool, thanks.
All right, if there's no other questions online or in the room, can we just thank Sam one more time, please? This excellent talk. And yep, if you want to get in touch with him, you can do that through Pete or me, and we can send you along. Thanks so much, Sam. Talk to you soon.
Thanks all.